So hello, folks. And to start off with, are there any like specific questions about the material that we covered? Yes,
I'm pretty good. There is one question I have when we get to the limits of just she solved a problem on the Friday video and I didn't understand how she did something, but I'll hold off until we get to limits.
Cool. Did you guys talk about limits this week?
Yeah, we had a little bit, just sort of briefly, where it's like the limit of...
Oh, the focus on theory.
Yeah.
Yeah, okay. For sure. Okay. In that case, we are gonna just quickly go over 2.4 and talk about 2.5 because we already have Casey saying that the marginal cost and marginal revenue isn't quite like conceptually there, and then we're gonna talk about limits, and that sounds like a day. So is everybody like cool with the second derivative, like as like a concept?
Yes.
Cool. Anybody else? Nobody else is saying anything. I'm assuming that, okay, that's actually good. Let's just do a couple problems with the second derivative just to like make sure that everybody's like on the same page. Let's start with number 2. So this is page, oh, that's a really weird looking P. That's okay. This is page 115, and we're going to be doing problem 2. At one of the labeled points on the graph, both dy dx and d2y dx squared are negative. So this is the first derivative and the second derivative. dy dx and y dx are negative. How would you guys solve this problem? I did it in 2 parts. First, I asked myself, where is the derivative negative? And can somebody tell me what points the derivative is negative at? Looking at figure 2.4, 40, 2.40. Okay. Yeah, but right now we're actually just looking at the regular derivative. This is kind of like last week material. So where is the first derivative negative?
The first derivative would be negative at A because it's starting to go down.
Yep.
And then there's another one. There's a second one.
Yep, it's A and E. The chat box was talking about that. Okay, so those are the only 2 points out of all 5 of them where the derivative is negative, because at B and C it is positive, and at D it is 0. So I've knocked 3 different points off of my list. Then I ask myself, where is the second derivative? Negative. And so I'm only choosing between A and E. So I have to look at A and I have to look at E and determine where the second derivative is negative. And as I think Casey put it, the concave down represents kind of like a negative second derivative. So the answer is going to be E. Can anyone tell me like why A is a positive derivative? Or second derivative, excuse me. Oh, go ahead.
Is it because it's beginning to get the curve up?
Yeah. Yep, concave up. That is one way of thinking about it. The way that I think about it is, so here we have a point that's like, this is our tangent line, and then here we have a point where this is our tangent line, and the slope of these tangent lines is getting closer and closer to 0. So because these slopes are becoming less less steep, the second derivative is going to be positive. And that's just kind of how I like to think about things, is like imagine these tangent lines here and see what they're doing. Okay, so you guys did that really well. Let's do number 6.
Question. Problem number 2. Let's say there was a point in between B and C. That point would be equals the F double prime equals 0, right? Isn't that where?
Yeah. So that's in the inflection point is what it's called. Okay. If it's like, it's right here, right?
Yeah.
Okay. So that's where the the slopes are getting more and more positive of the tangent line. They're getting bigger, and then they start getting smaller. And so the point at which that happens, this is where F double prime is 0. Yep.
Cool.
All right. Let's give number 6 a try. Here we kind of have like a line going on. Who wants to tell me? All right, what is the sign of the first derivative? And what is the sign of the second derivative? Any volunteers? All right, negative for the first derivative, exactly. Because it's just like sloping down. F double prime? Yes, exactly. Because it's a line. Exactly. All right, the slope doesn't change, so there is no like inflection point or anything like that. The second derivative is just going to be 0. That's perfect, guys. Okay. What about 12? Can we do 12 really fast? We have a table now giving us T and W of T. The first derivative, is it positive or negative?
The first derivative is positive.
Okay. Why do you think that?
Isn't it because T is increasing steadily?
Okay. When we think about derivative, we're thinking about, okay, so there's like something going on here. So as T increases, what is happening to W of T? So the derivative is talking about what is happening to W of T. If it looks like this, then the derivative would be positive. If it looks like this, the derivative would be negative. So one thing I like to do is kind of like graph it out in my head a little bit and say, okay, so I know my first one, T is equal to 100. Oh, so this is 100. And W of T is equal to 10.7. So this is like 11 or whatever. And here's my point. Okay, then my next one, T is equal to 110, and W of T is equal to like 6.3. So 6 is there, then this graph is like kind of meaningless because I have no like scale or anything like that on the sides. But the point is that it's going down. So our derivative is going to be negative. Yes. Casey, you're right. I, at least, always need to kind of visualize it. So yeah. If you really just wanted to do directly from the table, you could look at it and say, as T is going up, so T is going from 100 to 110, W of T is going from 10 to 6, so W of T is going down, which would also indicate the first derivative is negative. Okay. Getting the second derivative from the table, again, I would like kind of like think about it in terms of like how can I visualize this. I go ahead.
No, continue. Sorry.
No, it's fine. So there's like 4 or whatever. There's 3. Okay. So, and then it's like this, and then it's like this, and it's like decreasing like less and less. So it looks something like that. So we see this kind of curve looking here. Obviously this is like a very like sketchy looking sketch, but another way to look at it is, so I have my table that looks like this. And this is 10.7, 6.3, 4.2, 3.5. Okay, so T is increasing the same amount every time. The difference between this is, I don't know, approximately 5.
4.4, 2.1, 0.7, and 0.2.
That is exactly. Okay, so this is 4.4, and this is 0.2 when we're going from 140 to 3. Okay, so the difference between these two is larger than the difference between these two. The difference between these two is larger than the difference between these two, and it's like so on and so forth. So you can tell that if like, again, like kind of have to think of it in terms of like visualizing. So the slope is going to be steeper here than it is here of the tangent line. And so W double prime of T is going to be
Negative.
Yes.
Because if they had like the same, if they were decreasing by the same increments, that would be 0. If they were increasing by less and less, that would be positive.
If it was a line, it would be 0, and then it would look something like this if it was positive. So yeah. Okay. Okay. Actually, you're right. That was, yeah, you're right, Casey. It is positive. Reasoning is there, but I mixed it up. Thank you for calling me out on that. This, because it's approaching 0, it's becoming less and less negative, is going to be positive, not negative. Thank you, Casey. So, you're right. The reasoning remains that it's becoming closer, the slope is getting closer to 0, but that is a positive slope, not a negative slope, or a positive second derivative, not a negative second derivative. I hope I didn't confuse anyone on that. Okay. Yeah, you guys need to like call me out if I do something like that. Awesome. Is everybody cool with that? I didn't mess up anyone's. Okay. Let's move on to section 2.5 then. All right. Now this was talking about marginal cost and revenue. And we're going to be on page 122. And we're going to start by looking at problem 2. Or I guess I should ask, are there any more questions about second derivatives? Okay. Just want to make sure. All right. So problem 2 is saying we have this function that is C of Q. And that is the cost in dollars to produce Q barrels of olive oil. If we were to think of it in terms of a graph, we would have this being Q and this being C of Q. What are the units of marginal cost? And what is the practical meaning of the statement marginal cost is equal to 3 for Q is equal to 100? Okay. Where do I start with this? I would start by establishing units. The cost of producing how many Q barrels is going to be measured in dollars, and Q is going to be measured in barrels, yeah. So we're considering this as like a change, so it's delta Y over delta X, or in this case, dollars over barrels. So yeah, that is the units for the marginal cost. What is the marginal cost? Like very explicitly in this chapter, the marginal cost was defined to be the derivative of the cost. So we know that marginal cost is equal to C prime of Q. And okay, so the marginal cost is not actually equal to the cost of the 101st item. It's equal to the cost of the difference between C101 and C100. And the reason is because we're trying to figure out like how much more we have to pay to get 101 barrels. Like what is the cost of getting 101 in comparison to getting 100 barrels? So we have to think about it in terms of derivative. And it's important, especially like for this section, to like link these things. So marginal cost is C prime of Q, which is like the difference between the cost of like one more. And we're doing this in terms of units of one. This looks an awful lot like our average rate of change problem, right? Then it would be 101 minus 100 here on the bottom, which is equal to C of 101 minus C of 100 over 1, which is just, we can get rid of the 1. So that's why they write it like this. Okay, is everybody following me up to here? Cool. So what we need to do is we have established that marginal cost is equal to the derivative of Q. And we're saying that C prime of 100 is equal to 3. What that means then, we can think about it in terms of like conceptually, like we know that it's going to cost $3 more to produce this next barrel, but we can also, using this statement that we made, say that 3 is going to be equal to the cost of 101 barrels minus the cost of 100 barrels. So if we know the cost of 100 barrels, let's just call that, like, this is like a constant. So the cost of 101 barrels is whatever the cost of 100 is. I don't care what that is, it's just some number, plus 3. So it's $3 more to have 101 barrels instead of 100. Is everybody cool with how we approached that problem? Still a little confused. Okay. Let's rewrite some of this. Okay. You followed me up to this point. Let's make this generic. Ooh, that's not what I need. Okay. Let's give these some actual numbers. So let's say the cost of producing 100 barrels is, I don't know, measured in thousands. It's, now why would it be measured in thousands? Maybe it would be measured in thousands. No, it wouldn't be. All right, let's just call it, I don't know, 317. That's an unreasonable number, but that's what the number I picked. So we know that the cost of producing 100 barrels of olive oil is $317. We know that the marginal cost, which is equal to, given by the problem, the marginal cost for Q equals 100, so that C prime of 100 is equal to 3. So what I'm going to do is I'm going to move all of this down and put it into an equation. So I'm going to say 3 is equal to C of 100 plus 1, because that's the Q plus 1, minus 317. Because we've established that C of 100 is equal to 317. Is everybody cool with this so far? Yep. Okay. So then what I'm going to do is I'm just going to rearrange it because I'm trying to figure out like what's going on here. So I'm going to say, yep, C of 101 is equal to 3 plus 317, or 320. So the cost of producing 101 barrels is going to be equal to $320. So what I want to know is like what the marginal cost means. And what I like to do that, so we have this information saying the cost of 101 barrels is 320, the cost of 100 barrels is 317. The difference between these two is equal to $3, so it costs $3 more to get an extra barrel. Yes, Q is always just going to be the quantity. Okay.
Sorry, you made up those numbers, right? Because I don't get where you got that 317 from.
I made that up.
Okay.
I just thought it would be easier to like write down and like think about that.
Yeah. Okay.
So nowhere in the problem was 317 like in there, but as in terms of like visualizing it, basically the point of saying marginal cost is that it doesn't matter what it's like it's a way of saying that like it doesn't matter what numbers you give me. If I have an equation, I can tell you what the marginal cost is, like regardless of number. So, okay. Let's try problem 4. Okay. So we have this figure, 2.55. We're trying to figure out if the marginal cost is greater at Q equals 5 or at Q equals 30. And then we're also going to compare Q equals 20 and Q equals 40. And then we're going to like talk about explaining. So we have this graph. It looks something like this. It's not quite that flat, so I'm going to redraw it. If I can get my eraser to work. And, okay. Here is 5, 10, 20, 30, and 40. Something like that. Okay. So, thoughts. Our first question is marginal cost greater at Q equals 5 or Q equals 30? How would you start solving this problem? Start off with, you like recognize marginal cost is equal to C prime of Q. And like I said in the last problem, the point of like having like marginal cost as a concept is to say you give me any Q and I will tell you, if I have the equation, what the marginal cost is, like what it costs to produce one more of something. So we're going to be analyzing the first derivative of the function C of Q, which is given here. This is the function. And we're going to say at Q is equal to 5. So this is what is derivative of C at Q equals 5, or what is C prime of 5. So C prime of 5 is not going to be 0. It's going to be this positive slope here. And then I'm going to go and I'm going to say, I'm going to do the exact same thing. I'm going to say for Q is equal to 30. I'm going to be finding C prime of 30. And so C prime of 30 is like this. And then I ask myself, which slope is greater? Because these slopes at these points, we've established that this is equal to the marginal cost at Q is equal to 30. Yep. And the greater one in this case is going to be, yep, which is steeper, is the question. Okay. Exactly. All right. So now that we've established Q a 5 in this case, let me get my eraser working. I don't know why. Oh, there we go. Okay. Let's take a look at the other two. Does anyone want to take a guess? Q of 20 or Q of 40? Yep, okay. So we have one vote for 40. I would agree with you. So it looks something like that. Versus 20, which looks something like this. No, that's way too steep to be 20. It's much flatter than that. Something a little bit more like that. So obviously it'll be 40, and that's how you answer this problem. Now for the explain portion. Conceptually speaking, what this is telling you is that, okay, so it costs, the marginal cost here is small, which is good for business, because that means, I'm pointing to the green line, by the way, not the blue one. Because that means that to make, it's like, it looks like about this area where it's very small. That means making, looks like from 15 to 25. The cost for making each one is like the extra cost of making 16 instead of 15, 17 instead of 16. It's all very small, so you're not paying a ton extra. And one way that you can look at that is that this is the y-axis, and this is about 200. So you're paying about $200 for 15 and about $200 for 25. Like, give or take money, but because it's not exactly that, but it's still about 200. A little less, a little more. As opposed to if you're trying to get 30 versus if you're trying to get 40, because the difference there is going to be something like, this is like 225, and 40 is way up at like 400. So it costs a lot more per item if you're making 31, 32, 33. Is everybody cool with that, like conceptually, like applying this to marginal cost? Awesome. Okay, another thing is that consider this tangent line. So if I have this tangent line here at 40, like this is like supposed to be the tangent line at 40. It's very steep here, and that's saying that, like, okay, so if every item, for instance, if it costs, if the marginal cost, again, I'm making up these numbers, so this is just me making up a number. I'm gonna say arbitrarily that the marginal cost of making 40 is going to be, making 41 instead of making 40 is going to be $10. That means that this line represents like what it would cost, like what would be happening if it costs like $10 to make every like item. So like conceptually, like this, it has a slope of 10. And so if you were like making things, it would be $10 per item. You would move over 1 on the X and up 10 on the Y. So for every item, it costs $10. And so that is marginal cost. Okay. If there are no more questions about this, we're going to do problem 6. Okay. Okay. So for Q units of a product, a manufacturer's cost is C of Q dollars and revenue is R of Q dollars, with C of 500 equaling 7,200 and R of 500 equaling 9,400. The marginal cost of 500 is 15 and the marginal revenue of 500 is 20. What is the profit or loss at Q is equal to 500? Okay. This I think we did in chapter 1. Yes, these questions are very intimidating. Basically, what you have to do is break down what they want. What is the profit? You guys remember this equation? Profit is equal to the revenue minus the cost. So whatever you make minus whatever you paid to make it is your profit. We're just going to use that exact same thing. So our profit, when we're making 500, is equal to the revenue of making 500 minus the cost of making 500. In this case, this is given to us. This is 9,400, and this is 7,200, and I think this is, what, 2,200? Something like that. Yeah, that makes sense. So this is the profit of making 500. Okay, so that's part A. Does everybody remember off this from chapter 1? Awesome. Okay. So then, if production is increased from 500 to 501 units, by approximately how much does the profit change? Okay. We're going to start by doing this the long way. So, we know that marginal cost is equal to, and this is at 500, marginal cost is equal to 15, and marginal revenue is equal to 20. So, we can use this to say, in our equations, we said that marginal cost is equal to CQ plus 1 minus CQ, right? So we have 15 is equal to C of 501 minus C of 500. Or 15 is equal to C of 501 minus 7,200. Or the cost of making 501 objects is equal to that. Because we're just going to add here and here. Okay. So now we have the cost of making that. Now we're going to do the revenue. So here we have the marginal revenue is equal to 20. And the same thing, this marginal revenue thing, this is just R. So its marginal revenue is equal to RQ plus 1 minus R of Q. So that's 20 is equal to R of 501 minus R of 500. 20 is equal to R 501 minus 9400. 20. So R of 501 is equal to 420. Okay, then what are we going to do? We are going to put them together just like we did with profit. So the profit of making 501 items is equal to 9420 minus 721. Okay. Okay, so this is going to be 2205, right? Yeah, 2205. Okay. Yes. So the marginal revenue formula is the same as the marginal cost formula. So then we can take this and we can say, okay, so I know that the profit for 500 and I know the profit for 501. I can say, I'm just, give me a sec, move the chat box. I want to get this all on one page. So marginal profit is equal to the profit of Q plus 1 minus the profit of Q. And so we have the profit of 500 plus 1, which is 2205, minus the profit of 500, which is 2200. And so the marginal profit is equal to 5.
I have a question.
Yes.
So we had the marginal cost and the marginal revenue before. Couldn't we work from marginal profit equal marginal cost minus marginal revenue to just get the answers?
Exactly.
Okay, I just wanted to make sure.
Yeah, this is, I just went through it one way.
Okay.
Because I wanted to prove to you guys that it worked.
Okay.
But for sure. The next thing that is to be said is that marginal profit is equal to marginal revenue minus marginal cost. Because the change in profit is equal to the change in revenue minus the change in cost. The short way to do it is just doing it like this. So yeah. This is our marginal profit. If production is increased from 500 to 501 units, the profit changes by $5. You get $5 more if you do it like that. If you move up. So yeah. Yeah, if they did not provide you with the marginal cost and marginal revenue, you couldn't answer part B. Because you'd be missing too much information. Okie dokies. Are you guys feeling better about marginal cost, marginal revenue stuff? Do you want to move on to talking about some limits?
Actually, I would like to go back to 2.4 because I don't think that F double prime is positive. I went back while we were doing this and reviewed the lecture on Friday, and then I looked at 13 and a couple other problems, and I don't understand how if the function is positive, the F derivative is negative and clearly concaving down, how is that then a positive even if it's going towards 0? Because then we even said in problem 2 before that E was the only F double prime that was negative. Well, E would be the point on problem number 12 because it's gradually getting smaller and going down. And then like number 13, it's increasing, and that on the back of the book says it is positive as well. So I just don't understand how number 12 is positive also. And if it is in fact positive, I really need an example of what would be a negative F double prime, because it is driving me nuts.
I'm so sorry. I'm so sorry that I confused you. Okay. This is 12 and this is 13. 12 is not positive. 12, the F prime is negative and F double prime is positive. Okay. That I can say, like, I can check the answers right now. I will check the answers just to make sure that I'm right. Because there's no point in doing this if, where are my answers? God darn it. I know they're somewhere. Okay, give me one sec. I will go back. Section 2.4.
Because I have a little chart that we made too from the Friday lecture.
All right, so direct from the answer book, the derivative of W of t is negative, and the second derivative is positive. Okay, and then for 13, the derivative is positive, and the second derivative is also positive.
Or 0, which I didn't understand what that meant.
Yeah, we'll talk about that. So I'm just going to write this down for 13 so that I know to talk about it. Positive 0. Okay. All right. So, okay, we are going back to page 116. And we're talking about, this is 12 and this is 13. Okay, so we're going to graph this a little bit more explicitly. We're going to say that, all right, so this is 6, this is 0, this is 12. Okay. And then this is going to be increasing. This is 100, 110, 120, 130, 140. All right, so we have a point at about 10, or about 11, 10.7. We have a point at 6.3. We have a point at 4.2. We have a point at 3.5. And then we have a point at 3.3. So we've got a fairly defined curve that looks like that. Okay. So we start by saying, what is the first derivative? Well, we know that this is decreasing, so f prime, or excuse me, w prime of t is going to be, I'm just going to erase this. Okay. Okay, we're all good with that. So, when we were talking about problem 2 in this section, we said that referring back to problem 2 because you mentioned it, you were talking about point E, right?
Mm-hmm.
Point E, the first derivative is negative, and the second derivative is also negative. What this is point A. So what we're looking at is something that is, I'm trying to find a good, okay, so we're coming down, and like, I don't know what happens after this point, but for instance, it could go up. in that instance, this would be the point A of that. It would not be point E. Okay, that was a reference back to problem 2, just to like clarify that problem. What we're gonna do is we're gonna start and we're gonna draw the slopes of the tangent, or we're gonna draw the tangent lines at each of these places. So that's a very steep tangent line. That's a less steep tangent line, less steep, less steep, less steep. So this is very negative. This is less negative, this second one. This is less negative. This is less negative. This is approaching 0. So if something is getting less negative, it's getting more positive. So the second derivative, eventually we're going to hit this point where it's going to be a flat tangent line. The second derivative is going to equal 0, and then it's going to be able to come back up. And so these will become more and more positive. And so this is the concave down. Or no, this is a concave up, excuse me. Concave up, which we tend to associate with positive. So W double prime of T is positive.
Hey. Hey.
Is that your cat?
Oh, yeah, sorry, I thought I was muted.
I love her. Okay, so are we cool with this?
Yes.
Okay. So we have W prime of T being negative, W double prime of T is positive. So this was problem 12. Now let's do problem 13. So here we have this is 0, 1, 2, 3, 4, 5. And this is going from 12 to 55. So I'm gonna, that can be 60. And this can be 10. So this is 35. Something like this?
Yeah.
Okay, so it's 25, 12. 20, 30, I don't know, 40, 50, something like that. Okay. The graph is obviously not perfect, like scale-wise, but it's okay. So at t equals 0, we have s is equal to 12. So it's like right here-ish. Okay. At t equals 1, s is equal to 14. So also like right here-ish. 17.
The 0 is probably meaning between points 1 and 2, where they're increasing at equal interval 3 both times. Is that where they're getting that 0 from?
Yes, that is exactly it.
Okay.
You're saying that this is
a flat.
Yeah.
Or I shouldn't say a flat. It's a
linear. Yeah. So that's 20, and then here it gets up to 31, and then here it gets up to 55. So it's like whoop.
Yeah, that one I get. That one makes sense to be positive.
Okay, so we know that W or S prime of T is positive, and it starts off like close to 0-ish, and then it gets very positive, like very high. So S double prime of T is positive. Or perhaps 0, we don't know in this location. We don't know. Could be doing whatever, but okay. Are we good with this?
Yeah, that makes a lot more sense now.
Okay. Sorry about that. I wrote down the wrong thing and everyone got confused. So
No, I'm having a really hard time just picturing a negative though. But I guess if it were like increasing further away from zero, that's where it would be because it's going negative.
where is it going negative?
No, I'm just talking out loud.
Okay.
Like for number 12, it was slowly moving closer to zero and it was slowly growing, like less zero becomes more positive, wherever you said.
Yeah.
Okay.
That's honestly, I'll like, if I'm like working on a problem, I will draw out these lines and I'll say, okay, so it's negative here, it's less negative, less negative, less negative, and then I like make the transition to say less negative is more positive.
That makes sense. That is actually really helpful.
Okay. I'm glad. Okay. Cool. We ready to just talk about some limits? Okay. All right. This is now the review. We are doing the focus on theory. What page is this on? Okay. So this is like where the concept of like the derivative comes from. I'm assuming you guys like talked about this kind of stuff like in your class. Let's do problem 2. And we are using figure 2.77. Okay. Sorry, let me get situated. Okay, so we're on page 135, doing problem 2, and our graph looks something like this. And this is the f-axis or the x-axis, and this is the function. Okay. So these are basically like finding derivatives by hand, and it's, I don't know, it's like important to like understand conceptually where derivatives come from, but it's like a highly unnecessary step of like steps to take in terms of like solving an actual problem, if you understand. So it's important like for conceptual understanding, but not for solving problems. Okay. So we are going to mark lengths that represent the quantities in parts A through E. So pick any h with h being greater than 0. Okay. Do we say we go right here? So this is going to be, here, I'm going to do it underneath so that we have plenty of room in this graph. This is going to be A, or this is going to be H, not A plus H. And then A plus H is going to be this whole thing. So this is the distance from 0 to A is distance A. The distance from A to this point is distance H. So the distance from 0 to this point is A plus H. And we're just going to call this point H. Okay? Everybody okay with that? Okay. So that is part A. So then let's talk about what is H. In this case, it is just going to be, we're talking not about this point. This is, I'm going to call that H sub P. That's the point. this is the h. This is the distance from A to h. Okay. C is going to be f of A. So f of A is the point f of x where x is equal to A. And so that's right there. This is f of A. Because this is where x equals A. Then we need f of A plus h. So this, I'm rewriting some of this, if that's okay. This is not going to be point h. This is going to be point A plus h. So point A plus the distance h to get to point A plus h at point A plus h. This is going to be f of A plus h. We're good? Okay. Next, we need to do f of A plus h minus f of A.
I'll just say this makes a lot more sense, but I actually had no clue what the book was asking me to do.
Yeah. I'm not really sure what they want me to do, like in terms of marking things.
I mean,
But-
this what you're doing is making a lot of sense. And
Okay.
I could see that, but whenever I did it, I was like, I don't really know what they want.
So basically what we're doing here is we're saying that just like we were doing in chapter 1, keep in mind, so what did our generic formula look like for our average rate of change? What did we call everything? We just called it delta y over delta x, I guess. Delta y over delta x. In this case, this is like an average rate of change problem. Our delta x is going to be this variable h, and our delta y is going to be the change from this point to this point. So it's going to be, okay, so f of A plus h minus f of A. So this is f of A plus h, this is f of A. Whatever values are, you would subtract them, so it'd be like, I guess, negative. What I'm going to do is I'm just going to draw a line between them.
Because it's the slope, no?
Yeah. And so then what they want us to do is use your answers to represent the quantity f of A plus h minus f of A over h as the slope of a line on the graph. And so this is actually the answer not to E, but to F. Does that make sense? Because this is the line on the graph. For E, what I'll do is I'll just so this is the delta y, and this is the delta x. Okay. So taking a derivative is like theoretically exactly the same as finding an average rate of change. The only difference is that this h is a variable, and we're going to say h is getting smaller and smaller and smaller and smaller and smaller until it eventually is going to approach but not equal 0. So that's how we get, yeah.
Sorry, can you go over that last one, why it's not f of A plus h minus A again? Because I'm confused now.
This one, this f?
Yes.
Okay, so this is actually over h. And so basically the way that I think about it is I think about it in terms of like the average rate of change. So if I have a graph that looks like this, this point to this point, actually let's make it a little bit more dramatic. let's make the graph look something more like this. And so here is our A, and we're going to move H all the way out here. Okay? So we're going to go through and say that our f of A is here. Our f of A plus H is this point, because this is A plus H, not just H. I wrote that down wrong. I'm sorry about that. This is A plus H, f of A plus H. And then just like we would do, like connecting these points with a line, we can't, like, these are each numbers, so we can like subtract, like if we had like actual numbers, we could subtract f of A from f of A plus H and it would be a negative number, but we need to divide it by this distance H so that we can think about it in terms of a line, because this is distance H given by, like, down here.
Mm-hmm.
So this is delta X, and then this is f of A plus H, or f of A plus H minus f of A. So it's this, like, this drop from f of A to f of A plus H, which is also the delta Y. So what we need to do is, in order to find this chunk, we need to have f of A plus H minus f of A, so delta Y over delta X. In this case, it turns into f of A plus H minus f of A over H. And so this line that connects them, this average rate of change, goes straight from here to there. Okay?
Okay.
So you can see it doesn't exactly, like here it's not very clear that it doesn't follow the curve, but here, like it's trying to, like I'm trying to show you explicitly that it's not the curve, it is the average rate of change. And so what this, like, conceptually is doing, like what the derivative is conceptually doing, is saying, okay, so we have H that's way out here. What would happen if H was instead, this was A plus H, and this was H? So then it would be like that, right? And then, like, oh, what instead of that? Like, what if instead of that it was like here? And so we get closer and closer and closer to just being at A and it just being the tangent line to A. And so the derivative is like when H is like infinitely small. I believe the word they call it is like arbitrarily small. I don't know why they use the word arbitrarily. It always bugged me. But like you can make H as small as you want. And like the point is that the closer you get to A, the closer you approximate the tangent line of A. Or the derivative of A. Or the derivative of f of A. Okay. This is like the hardest stuff, I think, conceptually to like think about. Okay. Is there a specific type of problem in this section that you guys would like to do?
Yeah. It's specifically a problem she did that I don't see exactly on here, but the ones that look really close to it would be number 10 on page 136. It's kind of close.
Okay.
In her problem, basically, it was 3 plus h squared minus 9, and whenever she broke it down, she like added the 9 to itself and made it just disappear, and that's where I didn't understand.
Okay.
So
I guess I haven't actually seen her video, so I'm not sure what she did. But
the point too was because the limit is 0, that if you were to just plug in 0 to h, it would make the entire problem 0. But because we're trying to reach the limit, we don't want that. So we're trying to get rid of that h at the bottom.
Oh,
so
yeah.
that was trying to break it down.
Yeah. We can definitely talk about that because dividing by 0 is a big no-no. So as h gets like infinitely close to 0, that thing will just be like infinitely large. Because if you divide by like a really small number, it gets very big. So we need to get that h out of the denominator so that we can actually get a reasonable answer. Does that make sense?
Yes.
Okay. So we are solving these problems by substituting smaller and smaller values of h. So, gosh, okay. Did you guys learn about L'Hopital's rule? I'm trying to figure out like what tools I should use to solve this. So I'm putting it a little bit to you guys, like how you would start here. And if you aren't entirely sure, I am actually checking right now to see how they solve it in the book so that I can make sure that I give you the answers that you can actually work with. Okay.
Well, like I said, whenever she broke it down, she got rid of the exponent first by doing it in the parentheses. And then once she broke that down, it like turned that 9 into a positive, and then she added a negative 9.
I just looked at like how they want you to solve it from the book is like exactly like this is 3 plus 0.1 to the third minus 27 over 0.1. And so they just want you to like substitute in very small numbers. And then just keep doing that. And they did it 3 times. Just get progressively smaller. So they never actually moved the h out of the denominator because these all were getting approximately to, this is like 27.91, 27.09, 27.009 or something like that. And so it's getting progressively closer to 27. So the limit as h approaches 0 is said to be 27. Because as h gets closer to 0, it gets smaller and smaller and smaller, the limit gets closer and closer and closer to 27.
Which, that does make sense.
Yeah. So I'm not sure what algebra she was doing.
They were basically, the way that they taught us in the video lectures and on the Friday thing was that whatever the limit was, that was what you could replace with x or h. So that's why whenever you have limit to 0, you can't just put 0 into the problem you just did because you would divide by 0.
Yeah.
So then, as Casey said, she had to factor out that h, which then she somehow factored out that 9, which would in this case be that negative 27, and it just sort of.
Okay. Yeah, I understand. Okay, let me. Yeah, give me one sec.
But to be honest, I like your way just because. That's a little easier to understand.
Yeah. Well, the thing is that's time consuming. Approximating the limit is a little bit time consuming. Okay. To be honest.
What did Olivia do?
Yeah. Oh gosh. Honestly, I would probably do it by approximation because it's been forever since I've been simplifying limits. And it works. I'm looking at.
I looked at the question she did, and it seemed a bit different from this one. She had h plus 3 squared minus 9 over h.
So you said h plus 3 squared?
Minus 9. Is that the same question that they're talking about? Because that was the one I saw.
Okay.
And the limit to h was 0. Sorry.
Yeah, the limit.
Yeah. As h approaches. Okay.
But I think both of them were asking something different.
Oh, I see. Okay. So what they actually want you to do, so you couldn't have, like, they wouldn't have really expected you, I think, to do this for problem 10 because you had 3 plus h cubed. But what you can do here is you can say, like, you can expand this. You can say h plus 3 times h plus 3. This is h plus 3 squared. And then you FOIL. Yeah.
Yeah, that's what she did. But
why did that 9? Sorry, Casey.
Sorry, I think the question in the book is actually different from the question that she did. What it was actually asking of you.
10, they asked you to solve by approximating. 19, 20, and 21, and 22, they all ask you to solve by simplifying the expression. So why don't we do, we'll do 20 and we'll do 22?
Yes.
Okay.
That's closer to what she actually did. Oh, sorry.
During that FOIL thing, though, you turned your 9 after you broke it down into a positive 9. That's where I'm getting really confused because why is that being affected whenever you were just doing the exponent?
Okay, so this is
really simple math rule. I think that's
this is what I got, right? So this is the expression that you guys were asked to simplify?
Yeah.
Okay, so doing FOIL is a method of expanding this squared expression because if something's squared, it's just multiplied by itself, right? So we have h plus 3 plus h plus, or times h plus 3. So FOIL, you do the first, h squared, inner plus 3h, outer plus 3h, and then last plus 9. Did you guys do FOIL method recently in order to solve? And so basically this whole chunk is equal to h plus 3 squared. So what we're going to do is we're going to put that whole thing back in. So it's going to be
minus 9.
Yes. So h squared plus 3h plus 3h plus 9 minus 9 over h. So this is going to be h squared. These are going to cancel. This is going to be h squared plus 6h over h. Divide everything by h, and it's h plus 6 over 1. H plus 6.
Oh, because 3 squared is, oh, okay. Gotcha. I'm in now. Okay.
Yeah, you're all good.
Okay. That has been my roadblock since Friday.
You are all good. Okay, so we're going to do problem 20 and we're going to do problem 22. And what I'm going to do is I'm going to write these down and you guys are going to try to do them and tell me what you think about them in like 2 minutes. Okay? Okay. Thoughts on 20?
We know we can't plug that 0 in indirectly.
can't just put it in directly. This is something nasty. They put these parentheses here to make you think that like this is like some like secluded like chunk of information, but you can get rid of them because this is just to the 1. This isn't like squared or anything. So you can just rewrite this as 3h minus 7 plus 7 over h, and then those two will cancel. And so you end up with 3h over h. H cancels, so the limit as h approaches 0 is
3.
Okay. Here we also, this is squared, so we can't just get rid of the parentheses. So we have h minus 2. Do you guys need me to go over for you? Because I totally can.
That would end up being plus 4, which would cancel out the 4, because 2 squared is 4. So it's h squared. H, cancel that out. 4 is cancel
and then another way you can think about this is you can factor out the h on the outside. So this is actually h minus 4 times h. And then if you like put the h back in, it would be h squared minus 4h. And then you can just cancel the h's out like that. So it's h minus 4. So the limit as h approaches 0 is negative 4. Using this exact same problem in negative 2, or for problem 22, what would the limit be as h approaches 10 of
with this one, you could just plug in the 10 though and solve.
Yeah, you could. Or you can just, you've already solved and you have h minus 4. So it would just be 10 minus 4 or 6.
Huh.
Because what we stated was that this expression is equal to this expression.
Regardless of the limit.
Yeah. Regardless of what h is going to be. And the only reason we wrote it like the second version is so that we could actually solve it.
That makes sense.
Okay.
Cool.
Awesome.
Foil that was spoiling me. But
Okie dokies. Are there any other questions?
I'm personally good.
Okay, awesome. Feel free to email me at all. This limit stuff, I think, is like, this is like about as conceptual, I think, as this class gets when you're like thinking about like what's going on with the limits. But thinking about it in that conceptual manner will make it easier for you to understand like what's going on with the derivative, like what, like how do you work with derivatives. Chapter 3, like this next week for you guys. Just finding a lot of derivatives over and over and over again, which gets really tedious, but it is like the way that you get good. So,
good.
Yeah. So we can talk next week about derivatives. Cool. Okay. I guess I'm gonna let you guys go if you don't have any more questions. You guys have a great day.
Thanks, Olivia.
Yep. See ya.
Bye, everybody.